okay. So, in the previous lecture we ended up here that your equation 18, right, and this is nothing, this is for my own reference, right. So, we got z dot is equal to d z, and D is a diagonal matrix, and each diagonal element is nothing but the eigenvalues of the matrix A, right. So, let me clear this. So, now equation 18 actually represent n uncoupled first order, that is scalar equation, right, because if you look into this equation, that your this equation z dot is equal to d z, generally if I write, I am just overwriting on it, just see this, this is say z 1, z 2 up to z n, suppose matrix is n into n is equal to this d is actually diagonal matrix lambda 1, lambda 2, lambda n into your z 1, z 2 up to z n, right, and all other elements are 0. Therefore, z 1 will be equal to lambda 1 your z 1 dot, z 2 dot and z n dot, right. So, z 1 dot will be equal to lambda 1 z 1, z 2 dot will be lambda 2 z 2. So, it is only z 1 dot is function of z 1, there is no this thing, no other z's are appearing. So, completely decoupled, right. So, because of this, then this equation that we can write then for I state variable, say we can write z I dot is equal to lambda I z I, right. I told you before that actually your what you call lambda is like this, but my habit has become to write like this. So, I hope you will forgive me for that, right. So, so we can write that z I dot is equal to lambda I z I for I is equal to 1 to n. This is actually equation 19, right. Now, equation 19 is a simple first order differential equation whose solution with respect to time t is given by, right. If we want to get the solution, so it can be given as z I t will be z I t is equal to z I 0 e to the power lambda I t. This is actually equation 20, right. So, this is nothing, this is for my own reference. So, where z I 0 actually the initial value of z I, right, and now returning to equation 15, the response in terms of the original state vector is given by, right. So, when we come back to equation 15, right, you come back to equation 15 here, right, this is actually delta x is equal to phi z, right, that is equation 15. So, and we have got the expression for z. So, therefore, we can write that in terms of actually delta x is equal to phi z, that is true, but it is a time function. So, same equation we can write delta x t is equal to phi z t, where delta x t is equal to phi 1, phi 2 up to phi n, and this is z 1 t, z 2 t up to z n t. This is equation 21. This way you can write that delta x t in terms of z 1, z 2 up to your what you call z n t, right. So, which in view of the equation 20 implies that delta x t will be equal to sigma I is equal to 1 to n phi I z I 0 e to the power lambda I t, because the solution of your z I t is equal to your z I 0 e to the power lambda I t in general, and here you have phi 1 z 1 plus phi 2 z 2 and so on. Therefore, it can be written as sigma I equal to 1 to n this phi I, and your z I t, I mean in general here I am putting in general that your z I t is equal to z I 0 e to the power your what you call lambda I t, right. So, this z I t we are replacing by z I 0 e to the power lambda I t, and this is I is equal to 1 to n the summation, right. So, therefore, equation 21, I mean this that means this equation 21, right, we have z t is equal to phi inverse delta x t. I mean from this equation 1 you can get z t is equal to phi inverse delta x t. I mean both side of this equation if you multiply by phi inverse, and then this is also phi inverse phi identity matrix, that means my z t is equal to phi inverse delta x t, right. So, that is what we are writing here, right. So, z t is equal to phi inverse delta x t, but we know that your phi I is equal to identity matrix. So, phi inverse is equal to psi, right. So, here we are substituting that your phi inverse, we know that your phi psi is equal to I, right. Therefore, phi inverse, right, is equal to psi, that is we are substituting here. So, z t is equal to psi delta x t, this is equation 2, this is nothing for you, this is my own reference. Therefore, this implies that z I t is equal to psi I delta x t, because your what you call in general, this is z t is equal to psi delta x t, but for I state variable say z I t is equal to, I mean this equation can be written as for I state variable z I t is equal to psi I delta x t, right. So, let me clear it. So, with t is equal to 0, it follows that z I 0 is equal to psi I delta x 0, because initial condition. So, here if we put t is equal to 0, z I 0 will be psi I delta x 0, right. By using C I to denote that scalar product C I is equal to say z I 0 is equal to psi I delta x 0, then equation 22 may be written as, that means this we are assuming that this is z I 0, we are assuming C I is equal to z I 0 is equal to this one psi I delta x 0. Therefore, equation 22 it can be written as, right, it can be written as your, I mean here it is, this equation 22 it can be written as your delta x t is equal to sigma I equal to 1 to n, then phi I C I e to the power lambda I t, right. So, it is z I your, because C I is equal to your z I 0 is equal to psi I delta x 0. So, this is actually delta x t is equal to I is equal to 1 to n phi I C I e to the power lambda I t. This is equation 26. In other words, the time response of the I state variable is given by, right, I mean if you expand this one, it will be delta x I t is equal to phi I 1 C 1 e to the power lambda 1 t plus phi I 2 C 2 e to the power lambda 2 t up to you come plus phi I n C n e to the power lambda n t. This is equation 27, right. Then the response actually depends on the all the eigenvalues, function of all the eigenvalues, right. Now, equation 27 actually gives the expression for the free motion time response of the system in terms of the eigenvalues and left and right eigenvector, right. So, one is that your phi is the left eigenvector and C 1, if you come here that C constant also function of psi I, right. So, this response actually function of both left eigenvector and the right eigenvector, right. So, thus the free or initial condition response is given by a linear combination of n dynamic modes corresponding to the n eigenvalues of the state matrix, right. Now, the scalar product C I is equal to psi I delta x 0, it represents the magnitude of the excitation of the ith mode resulting from the initial condition. This thing should be in your mind, that the scalar product, that is C I is equal to psi I delta x 0, actually it represents the magnitude of the excitation of the ith mode resulting from the initial condition, right. Therefore, if the initial conditions lie along the jth eigenvector, right, the scalar product psi I delta x 0 for all I not is equal to j are identically 0, right. I mean if the initial conditions lie along the jth eigenvector, the scalar product psi I delta x 0 for all I not is equal to j are identically 0. Therefore, only the jth mode is excited. Now, if the vector representing the initial condition is not an eigenvector, it can be represented by linear combination of the n eigenvector, right. The response of the system will be the sum of the n responses. Therefore, if a component along an eigenvector of the initial condition is 0, the corresponding mode will not be excited. So, little bit of little bit of understanding and little bit of practice is necessary. We will take altogether I believe 3 or 4 examples we will take later, right. Next is that eigenvalue and stability. The time dependent characteristic of a mode corresponding to an eigenvalue say lambda I is given by e to the power lambda I t. This we have seen, the response is function of that. Therefore, the stability of the system is determined by the eigenvalues as follows. This you know that a real eigenvalue corresponds to a non-oscillatory mode, right. A negative real eigenvalue represents a decaying mode. So, a real eigenvalue corresponding to a non-oscillatory mode, real eigenvalue that means if its real part is positive, right, and a negative real eigenvalue represents a decaying mode. The larger its magnitude, the faster the decay. A positive real eigenvalue represent aperiodic instability, right. The values of C constant, that is C's, and the eigenvector associated with the real eigenvalues are also real. So, I mean one or two things you have to keep it in your mind, the values of C's and the eigenvectors associated with the real eigenvalues are also real, right. Now, the complex eigenvalues occur in conjugate, that is true, right. So, in conjugate pairs, and each pair correspond to an oscillatory mode. Now, the associated C values and eigenvectors will have appropriate complex values, so as to make the entries of x t real at every instant of time. For example, here it will be something like this, a plus j b into e to the power sigma minus j omega t plus a minus j b e to the power in bracket sigma plus j omega t, right. So, this is actually it will come in this form. Now, next is your, just hold on. So, therefore, that equation that your a plus j b e to the power your sigma plus j omega t, then into plus a minus j b e to the power sigma minus j omega t, that is it can be written in this form e to the power sigma t into sin omega t plus theta, right, which represent a damped sinusoid for negative sigma. The real component of the eigenvalues gives the damping and the imaginary components give the frequency of oscillation. This you know from your third year control system studied, right. So, a negative real part represents a damped oscillation, whereas a positive real part represent oscillations of increasing amplitude, that means it makes the system unstable. If real part of the eigenvalue is negative, means in general it is stable, but if real part is positive, then it is unstable, right. Thus, for a complex pair of eigenvalues we can write say lambda is equal to sigma plus minus j omega. This is equation 20, right hand side all these things, this is for my own reference. So, the frequency of oscillation in hertz then can given as f is equal to omega by 2 pi. This is actually equation 29. This is not for you, this is for my own reference. The frequency of oscillation in hertz is given by this, you know that omega is equal to 2 pi f. So, f is equal to this much omega by 2 pi. So, this actually represent the actual or damped frequency, right. Next is that the damping ratio, that also you know from your third year control system, that is g xi is equal to minus sigma upon root over sigma square plus omega square. This is equation 30, right. Now, the damping ratio xi determine the rate of decay of the amplitude of the oscillation, right. So, the time constant of the amplitude decay is 1 upon mod sigma, this also you have studied, right. So, in your third year control system course, undergraduate course, or in some other control PG, if you have studied linear control theory, there also you have studied this. In other words, the amplitude decays to 1 upon e or 37%, this also you know, right, of the initial amplitude in 1 upon mod sigma second, or in 1 upon 2 pi xi cycles of oscillation, right. This also you have studied, but just your what you call, just to your what you call our just recall all those things, right. So, revisit, I mean we have to revisit certain things, right. So, you can recall it from your memory and just have a look in the your what you call that your third year control system, that chapter, right, overshoot, undershoot, all sort of things, it is given, any book, any standard book you can follow, right. So, now this is and up to this, right. So, this is not for you. I did not bring this one, I thought there is no need. This is actually not for you, this is not for you. So, this is not for you, right. I did not bring those diagrams, I thought there is no need, right. So, next is so this no question of figure 1 shows, no figure is given. So, I just deleted that one. Next is let us take one example. So, this example actually if you look into that, it is single machine infinite bus system. It is a there are 4 generating units each having 555 MVA. So, that is why it is 4 into 555 MVA, right, and 224 kV and frequency is 60 hertz. This is the terminal voltage E t, this is low tension side, that is L t, H t is the high tension side. This is power flowing, this is real power, this is reactive power, data will be given, and this is the transformer only reactance is considered J 0.15 per unit. This is a double circuit line, a double your what you call, then this is your J 0.5 per unit reactance, this is circuit 1 and this is J 0.93 per unit circuit 2 and this is infinite bus and voltage here it is E b, right. So, now the problem is given like this. Now, let us see. Now, the network reactances shown in figure are in per unit on 2220 MVA 24 kV base, because 555 into 4 is 2220 MVA, referred to the LT side of the step up transformer, the low tension side, right. Resistances are assumed to be negligible, we have not considered resistance, we have neglected it for the easy calculation, right. And the objective of this example is to analyze the small signal stability characteristic of the system about the steady state operating condition following the loss of circuit 2. That means, the objective of this example is to analyze the small signal stability characteristics of the system about the steady state operating condition following the loss of circuit 2. That means, suppose there is a fault and circuit 2 is totally disconnected, right, and the post fault system condition in power unit on the 2220 MVA 24 kV base is as follows: P is 0.90 per unit and Q is 0.30 per unit, that is over excited, that is your per unit, that is over excited condition, right. So, and this terminal voltage E t is given 1 angle 36 degree and E b is given 0.995 angle 0 degree all per unit. That means, that circuit 2 there is a loss of your what you call circuit 2 or circuit 1, just let me have a look that circuit 2, right. So, this circuit, suppose there is a fault and this circuit is out, this circuit will not be there. So, finally, what will happen, the basically circuit is like this, and this is infinite bus, this circuit is out. Therefore, total reactance of the circuit will be 0.5 plus 0.15. So, J 0.65, right. So, this equivalent diagram is given. So, in this case your now you have to find out, write the linear, I will come to that circuit, write the linearized equation of the system, determine the eigenvalues, damped frequency of oscillation in hertz, damping ratio xi and undamped natural frequency, that is your omega n for each of the following values of the damping coefficient in per unit torque per second, right, per unit speed. That is, one is case A will be A d is equal to 0, case B will take K d is equal to minus 10 and case C will be K d is equal to 10, right. These 3 conditions. Now, for the case with K d is equal to your 10, you have to find out the left and right eigenvectors, determine the time response if at t is equal to 0, delta t is equal to 5 degree and delta omega is equal to 0. These are the initial condition is given, that at t is equal to 0, delta is equal to 5 degree and delta omega is equal to 0, and for the case for K d, the damping coefficient K d is equal to 10, we have to find this, right. So, let us see the equivalent circuit. Now, the solution. So, these parameters are given, right, these parameters are given, that if you look into that, x d dash was given 0.3 per unit. So, this is actually your x d dash j 0.3, E t was given 1 angle 36 degree per unit, and this transformer also given j 0.15 because circuit 2 is out, right, and this is the line reactance j 0.5, and this is actually E b is equal to 0.995 angle 0 degree. This is infinite bus, and this is your E dash delta, right, voltage behind x d dash. This is E dash delta. So, our objective will first you have to find out the delta. Now, to solve this problem, that of course, every meaning is same. For example, to solve this problem for easy calculation, this is actually given that E t is equal to 136 degree and E b is given 0.995 angle 0 degree, right. So, now if you take my E t as a reference, E t is equal to say if I take 1 angle 0 degree, right, then this E b will be your what you call 0.995 then angle minus 36 degree, right, because that ultimately either E t is leading E b by 36 degree or E b lags from your E t your 36 degree. Now, right. So, meaning is same, both are same. If I take this is 1 angle 0, then it will be minus 36 degree. Now, if you draw for your further understanding, if you draw the phasor diagram, suppose this is my reference line, right, and this is your E b is equal to your 0.995 angle 0 degree. Therefore, this is my E t, right, and this angle is 36 degree, right. This is E b and this is this E t is equal to 1, right, this E t is equal to 1. Now, if you rotate the phasor, I mean if you bring this one as a reference, rotate the phasor like this and bring it reference, so it will go down. So, if this is my reference E t, if you take 1 angle 0 degree, then this one will become automatically, this will be by E b and this angle will be 36 degree. So, meaning is same. This actually help us for your easy computation, right. So, that is why your this is that is why we will follow that one, right. So, figure shows this one. Now, with E t as reference, that is why with E t as reference, right, this E t we have taken as a reference. Just now I told you the stator current is given by P minus j q is equal to E t tilde conjugate is equal to I t. That means, this is actually this is my okay, come back to that come back to this your what you call this figure. This is my E t, right. I take E t tilde say, and power was given P and Q both were given here. This is P and this is Q were given. So, you know from load flow studies, right, that power injection P minus j q, we can write that E t conjugate and current flowing through this is I t. So, this is actually I t, right. That means, my I t will be P minus j q divided by E t conjugate, right, and P I think is given 0.9 and Q is equal to 0.3, right. So, if you come back to this current equation, then that I t tilde your I t tilde is equal to P minus j q upon E t tilde conjugate. So, it is 0.93 minus j 0.31. So, it is nothing but your what you call, we have taken your E t as a reference, that means E t tilde is equal to 1 angle 0 degree, right. That means, this is actually 1 angle 0 degree. So, this is nothing but 0.9 minus j 0.3 per unit, right. Next, just let me clear it. Next, if you come back to this your what you call to this figure, that means, from there also you can write that my in general my E dash tilde is equal to say E t tilde in phasor form plus j I t then x d dash, because this is my x d dash and current flowing through this is I t. Therefore, E dash tilde will be E t tilde plus j I t your x d dash, right. So, that is why we are writing that your E dash t tilde is equal to E t tilde plus j x d dash I t. Now, E t tilde we have taken as a reference 1 angle 0 and this one is j and x d dash is given, no, x d dash is given here, that is your 0.3, right. So, it is 0.3 into that I t tilde we have got 0.9 minus j 0.3. If you do so, then E dash tilde is actually 1.123 13.9 degree, right. Now, if you draw the phasor diagram, I am making it here, say this is we have taken reference, this is my E t, right, this is E t. Now, E dash actually it is positive angle leading. So, it is actually this angle say 13.92 degree, right. This is my E dash, your what you call sorry, just hold on, it is E dash tilde, right, and this is my E t, and E b as E t has taken reference. So, this is my E b, right, and this angle is 36 degree, right. Therefore, this E dash tilde leading E b by how much, that is 36 plus 13.92 degree, right. So, that means 49.92 degree. I hope it is understandable to you, right. So, therefore, the angle by which E dash is E b, I told you it will be 13.9 plus 36. So, 49.92 degree, right. Now, the total system reactance is, that is x d dash plus your transformer reactance 0.15 plus line reactance 0.5. So, total is 0.95 per unit, right. The corresponding synchronizing torque coefficient equation, actually we know the synchronizing torque coefficient, this equation number I have forgotten, because you just go to those swing equations, right. You go to that topic where I covered, I mean maybe few lectures back, swing equation, there you know that that your synchronizing torque coefficient, right. And I put a question also, why it is called synchronizing torque coefficient. You will put this answer into the forum when you will go through it, right. So, question is that this one E dash E b. So, this equation number I have forgotten, I have written, but I forgot to write it, but you know that k s is equal to E dash E b upon x t cos delta 0. So, E dash is equal to, we got 1.123, E b is 0.995 and x t is 0.95, and delta 0 we got 49.92 degree. That means, Ks is 0.757 per unit torque per radian. This is a dimensionless quantity, right. So, linearized system equation also we have seen in that swing equation, that delta omega dot delta delta dot is equal to minus k d upon 2 h minus k s upon 2 h omega 0 0 delta omega upon delta delta plus 1 upon 2 h 0 atm. This equation we have seen before, right. I did not write the equation number, but same in that swing equation where we derived, the same equation is there. I mean same equation, we are just that linearized system equation that we are using here. Go back to that swing equation thing and your what you call and your this equation, right. So, now just hold on. So, this is actually earlier we have derived this equation, right. So, or that k d, we are using k d is equal to 10, value of h is also given, right, value of h is given, k s we have just determined, right. So, all these values you substitute here, and if you do so, that delta omega dot delta delta dot will be minus 0.143 k d minus 0.108, this is 377 2 pi f, f is 60 hertz you have taken, right, and this is 0 delta omega delta delta plus this is 0.143 is coming, this is 0 and delta T m, right. So, this is actually state matrix, it is 2 into to the simplest system. Thank you very much, we will be back.